organizes itself around these amphiphilic molecules, excuse me, not nonpolar. Water organizes itself around these amphiphilic molecules. If it was a nonpolar molecule, what would end up happening, instead of forming this nice circular shape, it'll form a flat layer. But bottom line, what these molecules do to water is they organize water. Water organizes around these things. What does that mean for entropy if something is being organized? Entropy is going to go down, is going to be more stable, okay? So when nonpolar molecules are thrown in water, or when amphiphilic molecules are thrown in water, water becomes more ordered, so entropy is going to go down. All right, more stuff here. Micelles are made of amphiphilic molecules with exactly one tail for each one of these. That's why you see only one zigzag line for each one of these. I bring that up because a liposome, unfortunately, it's very hard to see, but a liposome is made of amphiphilic molecules with two tails. Okay, that's a subtle difference, but that small difference causes the difference between a micelle and a liposome. Yes?
Is the two tails and one polar head, correct?
Yes, both of them will only have one polar head. It's just that a liposome has two tails. A micelle only has one tail attached to it. Okay. Another difference, of course, is that liposomes are an example of a very simple lipid bilayer, right? There's a polar interior for a liposome and for a lipid bilayer. And there's a polar exterior out here. And that's because you have two amphiphilic molecules interacting with each other. That's this yellow stuff here. The two tails from two different amphiphilic molecules are interacting with each other. This is how cell membranes are made. They are lipid bilayers, two layers of lipids stacked on top of each other. Okay.
So two layers.
Mm-hmm. Yes, two layers, liposome or cell membrane is the same thing, or lipid bilayer. It's the same thing. Micelle is just one tail. Notice there's no, for a micelle here, there's no empty interior like for a liposome. A micelle is just internal, is nonpolar there. Okay. Let's see. Enthalpy of reaction. So, I won't spend too much more time on this stuff, so let me flip to it, and I will give you a very good example of a question you should work on. Oh yeah, by the way, I messed up. I didn't balance this right. So if some of you saw that, good job. You need to make sure the reactions will be balanced on the exam. So I was definitely just testing you to see if you balance this reaction. And to really test you, I made sure the answer was the wrong answer as well. So make sure you fix that, just in case you didn't notice it. But yeah, enthalpy of reactions. Please read the answer description I gave for the two examples up here, because you will definitely be given an enthalpy of reaction question. If you have any questions on that, just let me know and I'll give you more details. But this is a long question we don't have time for, and there's only one of these on the exam. 1 second. One thing I will stress again also is make sure you look at the very end where they ask you what is the energy per mole of reaction, or if it asks what is the energy per mole of, for example here, the reactant ethane. That changes the answer. If the answer on the exam is, if the question is asking you what is the energy per mole of reaction, that's a fancy way of saying just calculate the dissociation energy of this reaction and you're done. If they ask you what is the enthalpy change per mole of ethane, you do the total reaction process, and then you just divide it by what the coefficient of ethane is. So you just divide it by 2. There's a good practice exam question. I think it's some reaction involving NH3 where you do this, and a lot of people get tripped up because they don't notice that it's asking you what is the energy per mole of NH3 or something. So take a look at the practice. It was probably 2 moles, so the answer is you divide by 2 for that. There was a question over here. If it was asking for per mole of reaction, you don't. But
for 2 moles, and then I went to the professor and he said that's when you don't.
Per 2 moles, I'd have to see the context of the question. I can tell you. I can tell you no matter what that practice exam question says. The bottom line is that if it's asking per mole of reaction, just calculate the total. If it's asking per mole of something up there, you divide whatever the coefficient is for that thing. Yes, you had a question.
When you calculate the energy, you do reactants minus products?
Yeah, it's a little bit weird, and there's a general chemistry explanation for that I don't want to go into, but I think of it as just calculate the number for reactants, calculate the number for products, and then you do reactants minus products. The technical reason is because it's technically reactants plus negative products, but a bunch of people get confused over the double negative there. So I just say reactants minus products and don't overthink it after that. Okay? Yes?
Would we do a follow-up question saying if it's exothermic or endothermic?
Not for this class now. Okay. All right, moving on. Let's get to chapter 4. Let's see. Okay, yeah, so he wasn't lying and I wasn't lying too when you had to know the 20 amino acids, name, structure, 3-letter code, and the chemical classification of each of your amino acids. So you need to know, given an amino acid, if it's acidic, basic, polar, or nonpolar. And remember that in this class, glycine is considered a polar amino acid, and he corrects that on the PowerPoints as well. So make sure you know that. Yes?
I see that different everywhere.
The glycine part, yep, and it's because there is debate over that. For this class, you consider glycine polar, and technically the reason why is because I believe general chemists and organic chemists call it polar, and biologists call it nonpolar. Is the other way around? I can't remember. But for this class, you consider glycine polar. For if you're taking the MCAT, you believe whatever the MCAT wants you to believe it. For this. I've done this, yeah, I can't remember. Non-polar, sure. It might be non-polar right now. I don't know. You'd have to go look at some study guide for that. Okay, let's see. Yeah, so there's a bunch of stuff on here that I want you to study, and I stress for you to study when you're studying these worksheets, but there's a few things to really remember, and that every amino acid has an alpha carboxyl group and an alpha amino group. You do need to know the pKa's of those. Technically, they're given in the table at the end of the exam, but it makes things much easier if you know ahead of time that all alpha carboxyl groups have a pKa of 2, and all alpha amino groups have a pKa of 9. And that's stated several times in your notes, so make sure you know that. Let me make sure. All right, we'll do that. Okay, so, and it is on here also. There are certain types of questions they ask for amino acids and peptides. Those types of questions are like, what charge does an amino acid have at a certain pH? What is the isoelectric point of that amino acid? They may also ask, given a peptide, like a tripeptide or a tetrapeptide, what is its isoelectric point? And what charge, peptide, what charge will the peptide have at various pHs? Okay? So, if you were there for that SI session, I will go over it again right here. There's some shortcuts you can do to answer those styles of questions, and there will be each one of those 4 questions. What is the charge of an amino acid? What is the isoelectric point of an amino acid? And it will also ask what is the charge of a peptide? What is the isoelectric point of a peptide at various pHs? So, let's go through that. Okay. All right. Okay. Good. Okay. In order to answer any of those like charge and isoelectric point questions, and even some Henderson-Hasselbeck questions, the ones involving amino acids, you can do what I call make a charge diagram in order to help you answer these questions. So here's how you do that. There's a flow chart I have put on Canvas that tells you how to, that very quickly gives you a shortcut on how to make a charge diagram for any amino acid. So for example, if I had cysteine, and I go through that flow chart, I will find out that cysteine's charge diagram looks like this, and I'll explain it in a little bit. Okay, that cysteine's charge diagram looks like this, and I don't know the pKa's off the top of my head, but you would go look in there, and I believe it's something like 2, 6 point something, and 9. And this is what would be the charge diagram for cysteine. So now I'll go over how you make something like this. So, What a charge diagram is a shorthand notation for all the possible forms that cysteine could have. Because cysteine is a weak acid, it can donate hydrogens and accept hydrogens depending on what version of this amino acid that you have. Cysteine could be +1 charge, neutrally charged, -1 charge, and -2 charge. How do I find that out? Well, the quickest way is to go look at the pKa table at the end of your exam. You go look at cysteine and it will tell you how many pKa's it will have. For cysteine, it will list 2, I can't remember the exact number, I think it's something around 6 and 9, okay? That means there are 3 hydrogens it could possibly give up. You go look at the flow chart that I published on Canvas, and you will know that if something has 3 pKa's, it either looks like this, as I have drawn it, +1, 0, -1, and -2, or it can look like this, +2, +1, 0, and -1. However, for those who are studying, only what type of amino acids do you draw this bottom charge diagram? Only basic amino acids. And the reason why that is that basic amino acids are more positively charged compared to other amino acids because basic amino acids have an extra amino group in their side chain. So that's why they can be more positive than normal, okay? Cysteine and acidic amino acids, notice they go all the way down to -2, right? That is because, for example, acidic amino acids have an extra carboxyl group in their side chain. That pushes the overall charge more negative. For cysteine, does anyone know what functional group cysteine has that no other amino acid has? SH, right? It has an SH. This SH in its side chain can become S negatively charged. So that's why the charge diagram for cysteine jumps all the way down to -2. It's acting like an acidic amino acid. It's acting like it has another hydrogen to give up. Yes?
How come methionine can't do that?
Methionine, and that's a very good question, is not SH, it is SCH3 instead, and that methyl group cannot leave. Right? There's a question over here. Yes?
Well, other polar amino acids can.
Some of them, that's the annoying
I
part.
know, like, there are 6 of them, so which one is cysteine?
I don't know them off the top of my head. The shortcut answer to figure out if a polar amino acid has, you can draw it like this one up here, just go look at the pKa table. If it has 3 pKa's, that polar amino acid is going to be like an acidic amino acid. If it only has 2 pKa's, oh yeah, by the way, if something only has 2 pKa's, it will always look like this. If an amino acid has only 2 pKa's, it's always only going to be able to look like this. And we already know what those 2 pKa's are, right? 2 and 9, right? So that would be like for alanine or phenylalanine or something, yes?
Whoever's phone's at the front, it's not like recording because of like
Oop.
the power button.
Uh-oh, okay. It's fine.
No, it will still be recording.
Okay.
Just gotta click OK.
Uh, all right.
We're going to find out later.
This one's still recording, that's good, and I'm paranoid enough to check it every 5 minutes, so we're okay. All right. Because I know I'm going to get 300 emails saying, where's the recording? Okay. All right, let me make sure. So charge diagram. So making a charge diagram makes a lot of things really easy, such as if my question was, what charge will cysteine have at a pH of 7, you would tell me what? -1, because this, again, is the charge diagram for cysteine. At a pH of 7, we're right here. Cysteine should have a charge of -1. This question also makes it easier to calculate the isoelectric point of this amino acid. The isoelectric point formula is an average of 2 pKa's. Problem is if you have 3 pKa's to choose from, how do you know which 2? The answer is, you see the isoelectric form of cysteine, which is a fancy way of saying the neutrally charged form of cysteine. Here are 2 pKa's that are right next to it. So you would do 2 plus 6 divided by, or whatever the actual pKa is of this, I don't know it. 2 plus 6 divided by 2, that's the isoelectric point for cysteine. There's a question, yes?
So would he ask us like the charge at a pH of 6?
No, it will not do that. It will be on one side or the other of each of these numbers. Okay. Yes?
There was a question on one of your sheets, something like carboxyl groups, or carboxylic acid groups 4. methylation?
Oh, that was a reaction to amino acid, I think.
I'm not entirely sure what question that might be referring to.
If you should know, number 6, number
Here, I can look it up here. Which